Good morning, everyone. Welcome to Build 2016. Hope everyone got out last night to the party, and I'm so glad to see so many people come into the room this morning for the talk at 9 a.m., so thank you very much. My name's Dan Greco. I'm a senior software engineer with the Advanced Data Science Group in Cambridge, Massachusetts, right outside of Boston. We work on lots of different products or projects for external large international companies to bring them into the Cortana Intelligence Suite to set up pipelines for them, bringing data in, creating machine learning experiments for them to solve some of their business problems. I also have with me today Danielle Dean, who's the senior data science lead. There's Danielle. She usually comes to these talks to support me because she is a data scientist. She's also my manager. But I am I am an engineer on the team. We're made up of lots of data scientists and only a few engineers who support them to build the pipelines. So working with them over the past couple of years that I've been at Microsoft, I've learned a lot about data science and machine learning in particular. And in that process, I learned new terminology, how to do things differently or how the data scientists do it, which completely baffled me when I first started with them. And in that process of learning, I put this talk together to help other developers kind of come into that fold to understand how data scientists talk and give you a brief introduction to machine learning. In this talk, too, I'm going to do a demo. We're going to build a live ML experiment, and that's going to be towards the end. So as developers, we are used to solving problems. That's what we do for a living. We're given a set of a problem specification, and we use a traditional rules-based approach. We take in these data points. We know what we're supposed to produce for outputs. And we go ahead and write these rules engines baked into the application. We create that software, we deploy it, we deliver it out. And then at some point, we find out that maybe our rules engine could use an enhancement. We're not getting the right answers, and we have to go and we patch that and then have to redeploy it. With machine learning taking in some of this work, and particularly in Azure in the cloud, we build these experiments up in the cloud, and your application just calls it. It's a REST endpoint. You feed it in the input values, you get an output. If the model needs to change for any reason, we've got better data, whatever that happens to be, you can switch out the model up in the cloud, your software doesn't change. The endpoint remains the same, you might just get better, more accurate predictions when it comes out. So that's one of the real key things here with machine learning is it takes away that big rules engine and places it in the cloud. So what is machine learning? It's a term that's not widely understood. Some people think it's artificial intelligence, other people say it's robotics, or any number of things. So for this talk, it's important to figure out or to discuss how Microsoft feels about machine learning. And that's computers that become smarter with experience. And by that experience, we mean past data and human input. The past data is historic information that has come in. The human input comes from a number of places. Data scientists for sure, subject matter experts, to help go over that data, figure out what's important to go in, potentially do some other feature engineering work on that, tie in historic outputs to create what's called a training set. So we take that training set, apply algorithms to it to try and come up with a model that with a high confidence level gives us the predictions we're looking for. So in short, machine learning provides a powerful way to construct and study algorithms that learn from data as opposed to the traditional rules-based approach we're all used to. So in a sense, if we took an environment that had thousands of sensors, in our traditional approach, we'd estimate the conditions or sensor readings that lead to a failure and write our rules around that. With machine learning, we enable the computer to learn the relationships between the sensor readings and historic outcomes. So as we want to call that in the future, we get a good prediction back of what's about to happen. So as a data scientist or working with data science, where do we start? And that's going to be with the data. And when we talk about data, it's good to talk about how does a data scientist talk about their data and how do they view it. So we'll start from the top and work our way down. Training data is a set of samples. Really what it is, it's a table. You can think of it as a database table or a CSV file. It's just rows and columns. Your columns are your individual fields. A row in our table is called a sample. And a sample is just a single observation. So that is going to be your sensor readings. It could be your historic outcomes, engineered features that go along with it to create this table. A feature is an individual column in the sample set. And that's the data we feel that we're going to need to go into our model that's going to help us with the prediction. And a label is a historic outcome. And you may or may not have labels with your data, and I will talk about that later. But a label is the historic result in that single sample or observation that was the outcome from whatever the inputs were. So we can learn from that. So now that we have a little bit of a talk about that, we talk about human input. And this is really where the data scientist is going to come into play. So the data that has to be used or that you want to use for one of these models needs to fit these four things. It needs to be relevant, it needs to be connected, it needs to be accurate, and you need to have enough of it. So for example, if I take this glass and I have a cement floor here and I drop it onto that floor, you'll all have an answer of what's going to happen to that glass. And likely it's not because you understand the physics or all of the other information in the calculations that go behind determining if that glass is going to break, but you have seen so many things drop on so many surfaces over your life, you've built a model in your head. And that model tells you that glass is likely going to break. Your prediction is it's going to break. So with that example, and as you go over time, you see more things drop, you change your model, it retrains in your head. So to take these things into account, what's relevant here? The type of glass or the type of cup I have, the material it's made out of, the height with which I drop it, the surface it's going to land on, the initial velocity going down, and potentially whether it's full of a liquid or not. So that's all relevant. That's things that we're going to need for our model. What's not relevant? It's not relevant that I dropped it at 9 a.m. instead of 9 p.m. It's not relevant whether I had red or white wine in it. I only really care if it had a liquid in it. It doesn't matter if it's sunny outside or it's raining. Those things are irrelevant data, and that's where that data scientist is going to come in and clean those things out. So then we talk about connected. Connected really means if we know what our set of features are, do those features exist, or do we have holes in the data? There's models that can deal with some disconnected data, a few points missing here or there. But if I have a training set that only tells you it's a glass, wine glass, and it fell on cement, sometimes it broke, sometimes it didn't, but I don't give you the height, you can't build a model off of that. You don't have enough information. So that's a disconnected data set, and you need to figure out how to flush that out or use another set of data. Then we have accurate. In our case, it's from our observations. If we're tagging it with labels, did the glass break? Did it crack? Did it shatter? Did it not break? And in this example, it's very, very simple to figure out. So the accuracy and precision are your observations accurately tagged? And now we get to enough of it, and this is also just as important as the rest of them. So we have a model, we have a training set. All we've ever seen is glass wine glasses drop at 6 feet onto concrete. We know it breaks. Simple as that. Now someone else walks in the room and they have another glass and you see them hold it and they drop it and it doesn't break. It's plastic. Our training set wasn't complete. We didn't have enough data to know that our model was going to be accurate or it isn't going to be accurate, because we've never seen plastic come in. So again, now we have to have enough of that data to really say that our model is going to be trained. We can start with some model, and as we see new materials come in, new observations, we can then go back and retrain that model, make that model smarter to deal with more points of data coming in and give us better predictions in the future. So we talked a little bit about the data and the human input. Now, once we have that, we also need a question. What are we asking of our data? And that question needs to be a sharp question. Can we answer it with a name, or can we answer it with a number? What car in my fleet is going to fail first? It's a very sharp question, right? Which devices on my factory floor are going to fail in the next 30 days? Another sharp question. But a vague question isn't going to be able to be answered with machine learning. What should I do? How do I increase my profits? Well, you could work harder, put in 110%, but those aren't really good answers, right? That's not going to help you as you move forward. So you really need to come up with your sharp question and your data that you've worked with. So now we have our data, we've massaged it, we know we have the right stuff, we have a sharp question. So then we get into the question of the types of learning that a data scientist is going to perform. And there's really two types. There's going to be supervised and unsupervised. This goes back to what data do we have? In our training set, do we have historic outcomes tied to the historic inputs? In that case, we already know the field we're trying to learn, and it's a supervised learning case. There are other cases where we don't have the label, and in that case, it's an unsupervised. So we have to come up with a different approach here. Now, for an example, we have a factory, and we have 2 production lines in our factory. One's a legacy line, it's been there for 10 years. The other one's 3 months old. On the legacy line, we have lots of data, and we also have the historic outcomes that have some successes and some failures on it, and we tag it all. So that becomes more of a classification problem or a predictive maintenance type of problem that you need to solve. What devices are going to fail in 30 days? We feel pretty confident about that because we have enough data, we can train a model and figure it out. We go to the new production line that's only been running for 3 months, and it's always just been rainbows and unicorns. Nothing's ever gone wrong with it. So we don't have labels that tell us that it doesn't work. We only know the bounds that the line is working appropriately. So then we want to start looking at an anomaly detection, right? This is unsupervised learning. We don't know what the outcome is, but we can put in anomaly detection to say, hey, things are not running how I feel that it should be okay, and build a model that way. It may be a little less accurate than the predictive maintenance one or the classification, but it will work. So now we have problem detection, right? Again, all of this feeds down into itself. So what are we trying to solve? It comes down to what data do we have and the question you're trying to ask. Again, we have, can I group it, right? Are all of the viewers who watch this movie like this other type of movie? Those kinds of problems. We're looking for a clustering thing. Can you categorize it? Again, what device is going to fail in the next 30 days? Which of my cars in my fleet are going to fail first? So it becomes a classification problem. Then there's the questions of how much or how many. Given this vehicle taking this trip on this day with these other conditions, how many miles a gallon am I going to use? And then, is it weird? So that's that anomaly detection. We don't know. I mean, we don't have a label, so we only know that this is okay. So whatever just happened, is this weird? Is it something we haven't seen before? And then we can set up an alarm. And with any of these, particularly if you start talking about that anomaly detection or predictive maintenance, either one of them can then be built into a much larger system that feeds into, say, your SAP system or whatever it is that can create work tickets. So before you fire up your production line and watch it fail and lose $5 million of product in the day, you can send out your maintenance guys in the mornings to say, hey, this isn't looking right, or we know this device is having a problem. And let's go take a look at that one. Good. So we've talked a lot about data, using some of the terminology that a data scientist is going to use. So what do they use for tools? And because we're at Build, we're going to talk about the Azure Machine Learning Surface. It's all in the cloud, and this is the breadth of it. We have to have data to put up there, so we have it in blobs or tables, Hadoop, SQL servers, SQL data warehouses, wherever your data goes in. And then there's this great tool, which we'll get to next too, is the ML Studio. This is an online studio that the data scientist goes up, they pull in their data, they start working on their models, creating experiments. And when they feel that they've done their due diligence, then they can go ahead and publish a live REST API. And that live REST API then becomes consumable by clients everywhere. Now, in general, your individual devices on a factory floor aren't going to be calling in. They're probably going through a gateway. Does it make sense in a lot of cases to be making calls from an individual handheld client? Probably not. But you can do it because it's just an open REST API out on the web. But generally what happens in a larger production environment is it's built into the larger Cortana intelligence suite and the data that comes through. I don't know if you've been on talks about Event Hub, Stream Analytics, but you can call your ML from your Stream jobs that are feeding off your Event Hub, which is generally bringing in data, or later down the line, after you've done some other work, potentially all your files are getting created in storage, and you're using an HD Insight cluster to do some aggregation on the data before you process it. But again, it's just a REST endpoint in the end. And that endpoint can then be modified in the back end. Again, the model can be updated over time, which is some really powerful stuff there. So here we have the ML Studio, and I have the link to it right there. And I think the slides will be released and it'll be in there. So this is where the data scientist goes, or anybody can go. So ML Studio has a free tier, so anyone in this room can go to this link and log in and create it. In that free tier, there's some restrictions about how much data you can push up to that account and which endpoints you can hit, and I'll get to that a little bit later. But this is an online-only tool, right? You access it through your web browser. You don't have any software to install, so that's kind of nice. But you can collaborate with this with anyone, anywhere through an Azure workspace. So you go in, you're working on something, you either want to share your knowledge with a coworker, or you need your coworker to have a look at it because you're kind of stumped on something. You can invite them into your workspace to work with you. And in there, you can give them user access, so they can only read it, but they can't really delete anything or change it on you. Or you can give them full admin rights to help you work through your problem. Everything on here is a visual composition, so there's a lot of drag and drop of bringing out components to build your models. And there's best-in-class ML algorithms already built into the system. But there's times where they may not be enough for your data scientists or yourselves. You need to do a little bit more with the data as you're processing it. We have the execute R and execute Python modules in there, where you can bring those out and write in your own R code, your own Python code, and that becomes a module on its own. It will execute your R and Python code each time it runs through. And then, just as importantly, is that you can come up here and you can rapidly try a range of features or algorithms and modeling strategies to find that right solution before you go ahead and publish it as a service. So it's a really useful tool. Even I have figured out how to use it, so I think everybody else here would have a pretty good go of it. But that's the tool that the data scientists use. So I have an example here, and this is where we'll get into the demo, is we have a factory gadget. Let's see, okay, good. It's a contrived gadget. We came up with the data on our own, just to make it simple, easy to understand. Didn't want to do a lot of feature engineering here, because that's not what I'm here to teach you. I'm just talking about ML in general, data science, how these things get built, and we're going to consume it too. So our factory gadget, we have a factory of 100 of these gadgets. We've been recording data, whether the device is running successfully or it's running an error. And we built our training set. So from our training data, we have features here that are important to the device, the more important ones. So we have the temperature it's running at, the voltage it's using, its rotation speed. We also have a time field, but for us, we don't really care about having a date time field here. Just an integer field that increments over time is fine. A device ID, so we can identify a certain device. And then we have our label, and our label is a state. And in this case, 0 means the device is running okay, 1, it's an error. So it's just a two-state binary field, and we have this set with about 10,000 rows in it, I think, for our 100 devices. So here, I want to jump over now to ML Studio, and I hit the right button. Sweet. So here's ML Studio. We can see the experiments that I have in my workspace here. I have any web services that I've already previously published. I can have notebooks up here, Python notebooks, data sets, trained models, quite a few of them. But my data set is what I want to upload first. And just to make it easier for this demo, I've already uploaded that CSV file that I was showing you. It's my training data, and that's what we're seeing right here. So now we want to start playing with this, and we can look at the experiments. So we'll come down to this bottom corner, click New, and we'll see here that through Gallery, we have a plethora of choices of places we can start. These are other data scientists inside of Microsoft, some outside of Microsoft, that have created example applications that have the whole model built for you. You can go in, use it, tweak it, see if it works for you. But because we're doing a demo here, I don't want to start with one of those because I want to walk through each step and explain where I'm going. So we're going to start with a blank experiment. And the first thing we have is, so now we have a canvas here on this side, and I think I'm going to run out of space. So we're going to pull in our data set first. Because again, machine learning is all about data and data science. So we bring it out, we can see it's just an object, it's got one output port, so we can feed that into everything else we're doing. So the next thing I want to bring out is a split data. And this is important in the data science and machine learning world, is if we feed all of the data we have in our training data through our model that we're trying to train, we now overfit that model. It's great if we only have those values that come in, we'll get the right answer, but if things start to change a little bit, our predictions aren't going to be too accurate. So we want the data to be split. Half of it, or you can adjust that, but we're going to send half of it through our model to train and the other half to score against it to see how it works. Now you can see on the right-hand side, the split module has, how are we doing it? Well, we're going to split rows. What's the fraction out each of its ports? And we can modify this. And almost all of the objects we drag out on the canvas give us the ability to customize here. We don't have to go do custom code. The data scientist doesn't. They understand a lot of the things that are going on, maybe if I don't or you don't. But they know how to adjust these models. But we're going to leave this at a 50-50 split. And to get to the split, we simply just drag from the output port of one module to the input port of the other. I wish that would go away. Oh. All right, so the next thing we need to do is we need to train a model. So this is how we're going to build up our experiment. So we see it has 2 input ports, and we're going to send half of our data into the train model. But we can see it has a value required. Well, the train model is expecting us to have data that has a label associated with each of our inputs. So given that, the train model now has a column selector over on the right side. We need to tell it which of the columns that we have in our data is our label that we want it to learn on. And for us, we know that's state. But yet, train model still has another error. So, okay, right. It has no untrained model. So we have to figure out what we want to train it on. Again, we look at our data. What do we have? What are we trying to solve? And we're trying to solve basically a 2-state issue. It's 0 or 1, a binary field. Is it an error? Is it not an error? So we come over here. We know we have a 2-class thing, so let's type in 2-class. And we can see we get lots of different choices here. Now, I'm not going to get deep into why I'm picking a decision tree, because I got that help from one of the data scientists I work for, but we're just going with a 2-class boosted decision tree. And the important thing is, it's a 2-class because we have values of 0 or 1. So we plug this in to our train model. All right, train model stops complaining. Great. So now we need to score it. We need to know how the training is going. So we're going to bring out a score model. And we attach the training model to one port, but the scoring needs to know what data set it's scoring against. And that's where we pull in the other half of our data from the split right into the score model, and it's happy. But then we also want to evaluate how our model's doing, so we're just going to bring out the evaluate module out to our canvas. And here we are, we have a very simple experiment. We're training it, splitting out the data, training on a 2-class decision tree, and trying to see how we do for results. So we click run on the bottom, and run is going to run this graph for us, which usually takes a couple of minutes. Sometimes it's faster. Because I'm on stage, it's going to go really slow. But in my hotel room, it was lickety-split. But it does actually go pretty quick because we don't have a very complex model here. We don't have a ton of training data we're passing through. There's only 10,000 rows. It's absolutely nothing for this system. So we see all the green check boxes. We're in good shape here. So now we can take a look into evaluate model. Given the small screen size here, it's kind of tough, but we can come down here and see our results here. For data scientists, you know, this number right here, the area under the curve, is pretty important, right? And it's a 94%, so it's doing pretty well. We can see how many true positives, false negatives, what kind of accuracy this model was getting, its precision. It's doing pretty well. Could a data scientist massage that 2-class boosted decision tree to give us better results? Possibly. But again, I'm not here to talk about how you tweak those things. So we're going to say, yeah, this is pretty good. Right? For precision of 76%, accuracy 91%, we'll say it's good enough just so we can continue moving forward. So now that we feel that we've done the work, we've built the model, or we all seem to be happy with it, and this is what we want to do. So now we have to set up a web service. And down here, I have 2 options. One is a predictive web service, recommended, of course, and the retraining web service. Now, the predictive web service that's the endpoint you want all of your clients to call in to get your answers, whether you're calling it from Azure Data Factory or you're calling it from a client. That's the endpoint people are going to call. The other one, the retraining web service, is something you can set up to feed in new training sets. So as your data starts growing over time, you retrain that model, it'll overwrite the other model in the predictive service with a little bit of work, give you a new model in the back end, give you more accurate results in the future. But for us, we're just going with the predicted web service here. And we can see that it creates something. How do I get rid of that? It's driving me crazy. So we see that we have the outlines of what we need for our web service. So our trained model, and I probably should have gone and saved this with a better name because now my model and web service are going to be called Experiment Created on 4.1. So I could have renamed it and given it a better name, but I forget it a lot of the time. So at least I know when I made it. But we can see the module up here is our trained model. This is what our experiment has created for us. It feeds in data so we can give it a run here. But we have a web service input and a web service output, and this is what's going to get tied into our REST endpoint. Now, one of the issues here is that we know our training data has a label. It's telling us whether the device is in error or it isn't in error. If the device could do that on its own, we don't need a REST service. It could just talk to the gateway and say, hey, I'm having a problem. But we don't have that. We just had that in our training data. So what we need to do is now we need to massage this before we start doing it. So we need to project columns. And on the project, we're just going to take our training data, hook it to project, and the output for project is going to come into our score, which is our web service input. But again, now it's got a problem. It wants to know the value. Well, we just have to tell it the columns that we expect to be coming into our REST call. So we launch our column selector, and in our case, we want everything but state. The device doesn't know what state it's in. And that's what we're trying to figure out. So, okay, we've got that. Now on the output of the score model, yeah, we can't visualize it because we haven't run it, but whatever comes in to one of these services, all of your fields, are also going to come out with your output along with your predicted value and the probability score that you have an accurate answer. So we're just going to take out another project columns because we really don't want all of that coming out for this example. And again, so now project columns knows what is going to come out. And we can see, so we have our features coming in that we called it with. Then we get the scored label, which is going to be the predicted result. Is it in error? Is it not? So our 0 or 1. And the probability that we were accurate in determining it. But for us, we really just want to we want to know the time the call was made. We want to know the ID of the device, and is it in error, because then we'll use that flag to go into other back-end systems and create tickets. So we push those over, say OK. So now we have another graph here. And this graph, again, we're going to run it. And similar to the last one, the graph will run. It might take a few minutes, but again, we have a small set of data, a very simple experiment. It's not going to take long, except because I'm on stage, which is okay, because I think I'm going a little quick. And when we see this done, we can then also take a look at some of the outputs. So let's just look at the output of our project columns on our output. Is it what we expected? And it is, right? So we wanted to get out the time, the ID, and the scored label. So it looks like that's working as expected. So now we can click this deploy web service at the bottom. This is what's going to create the actual live Azure Web REST API for this that we can then share with anyone, anywhere, on any device. Assuming they have a network connection, can form HTTPS requests. They can call this, and they also need to understand the inputs, but we'll get to that. So we click deploy, and it's going to go through the back end now and push this out as a live service for us. You can see that it's now moved us down in the tree over here to web services, and again, it's got a really bad name, but we know I just created it. On this page, gives us a little bit of information about it. Here's our API key we're going to need. It also, at the bottom of the page, has request response and batch execution. For each of these, we can see that there's an Excel spreadsheet. So you can download those Excel spreadsheets, type in data to try it out, and it will actually call this service for us. The difference between these two is request response is taking a single sample. Well, they've adjusted it. You can pass in a couple of samples, but you're not sending in 10,000. But it's a synchronous call. I make the call to the REST endpoint, I get a result. My payload's going to be my output and what I expect from my output payload. Batch execution is an asynchronous call. So these are usually what are baked into some of the larger intelligence suite things like Data Factory, where data is being collected. So again, factory environment, I've got tens of thousands of devices calling in all day long. I don't really want to be calling the REST endpoint all day long because it doesn't mean anything to me. My line's already running. I need to run it once a day. At the end of the day, determine how does the line look then. So what I want to do is collect all of those readings during the day, store them off into storage, and then batch everything at once. Now you can write an application, and I've done it, that can call that asynchronous endpoint. But what you get back is just a job ID. And then you can turn around with that job ID, keep asking the service, hey, how's it going? Oh, it's still working, great. But when it finally finishes, hopefully successfully because your model works, it will give you the output file or location where all of your results, your scored results, have gone in. So on the free tier, you can go up and create all of these things, and you get these endpoints, but you can't use the batch execution endpoint. You can use the RRS one, but what you need to have is an Azure subscription because you need to tie it to a storage account, because that storage account is going to be the output location of your batch calls. So let's go take a look and see what we got for one of these services. So we get this page here. It gives us information about the service we just created. Here's the URI we have and the method we should call it with. It tells us about the headers in our payload or our request that we need to set up for it. And as we come down, it shows us the payload. And it's accurate. We said we're going to pass in our features, temp, voltage, rotation, time, and ID. And here's the example of the inputs, how they should look in your JSON payload. Again, you can pass in more than one sample. It used to be only one sample. It's multiple samples now. But again, I wouldn't go using this to try and do anything too large. I think the most I've done is 1,000 in one of these. If you're doing stuff like that, you should really look at batch execution. As we go down the page, we see our response. It's going to give us, well, what code can we expect? 200 is good. Well, it usually is. Our content type. And then it gives us the output payload. So this is what the JSON payload is going to look like when it comes back to you, so you know how to parse it. When you're using .NET, the JSON.NET makes this super easy, and it's consistent across your experiments. We'll figure out, it gives us information, what are our inputs, what are our outputs, but one of the great things is here down at the bottom of the page is we have example code. So we have the C# version, we have the Python version, R. So you can take this code and basically copy it into any IDE you have, execute it. For the C# one, we have to grab this one Web API client assembly, but it'll just work. For C#, the only thing you need to do is you come down here and you just need to replace this API key with the API key that is provided for your endpoint here. But this will work. You won't get any really good results out of it because the data that it's putting in is all zeros. But you can put it in quickly, build it, run it, see that your endpoint got hit, see that you got a result back out of it, and that's super, super helpful to figure it out. Batch execution similarly has a page that talks about batch and the differences of how you set up your payload to point it to your storage file that you want it to pick up. Here's your payload, right? It's an OK. This is your job ID. And then you can query along it. So you get these other endpoints down here where you can get the status or get the output. So it's a little bit different than the RRS endpoint. So you get some other things you can do there. But so we come back to the RRS. So because I've done this a few times, I've created an app. And this is my factory widget replicator. Not very fancy, just something that was whipped together that once I create my endpoint, I can come here and I can put in my API key in my URI, and then we can tweak with some of these features, the temperature, voltage, and rotation. We're always going to pass device ID 1, and the time just increments. It's an integer that keeps going up every time I make the call. So as a developer, what do I need? Well, I need my API key. And I need to get my RRS endpoint. Now I'm ready to make a request. And if the demo gods are with me, so we invoked my service with the URI, the key that we just got. Here's my inputs coming in. Here's my output coming out. 0 means I'm good. 1 means I'm not good. So it tells me my device is operating normally. But our device starts to get a little funky. The temperature starts spiking. And now we can see that it came back with a 1. This device is not doing good. But then, temperature goes back down. We should be OK. There we go. And you can play with the different things. But it's really just an example to show you how quickly, I spent way more time talking about building that module or that experiment than it actually took me to build it. It was very, very quick. We kind of understood the work. We had done the legwork to get the data together and understood what we wanted to do with it. We threw a model together up in Studio, tested it, felt like it was good, published it to a live REST service, and now I'm consuming it through this desktop client here. Client can be anywhere, but again, it was very simple to throw together a desktop app to do it. And now we can see that my poorly named experiment shows up here. My web services now contain another poorly named web service. But it did what I wanted. So we talked about data scientists, terminology they're using, how we talk about data, or how they talk about data, what kind of training there is, some brief talks about algorithm selection, and then go to build an actual module and consume it. Now, there's some other great resources here, and I believe they are sharing these slides after, or I think it'll be on Channel 9. But ML Studio, so again, there's the tool that you go up, you create your modules, you create your services, you manage them, play with them, whatever. Gallery is a great place. So when I went to do new experiment, there was a lot of things in Gallery there that were already like template projects for you to start with that you could move forward with. Now, as a developer, you may or may not want to build your own modules. So there's Marketplace, and you can go to Marketplace, and there, when you create an API, you can publish it and you can monetize it. It needs to be relatively generic and useful for other people, but we have one that's up there, which is a sentiment analysis. You just pass it in a load of text, and it tells you whether your user is happy, sad, mad. And those things can be really useful, and you get enough people calling it, you can make some money, but Marketplace is a great place to look. Now, I only had one more spot on here for the data science cheat sheet, but there's two really other useful talks for developers. Or one really useful talk, and this cheat sheet's a great one. But another colleague in the Boston office with us, Brandon Rohr, is really good about putting layman's terms around data science. Great data scientist. He has one talk that's already on Channel 9. It's called Data Science for the Rest of Us. He gets a little bit deeper into the relevancy, accuracy, enough data, talks about how data scientists talk about things, and he does some other stuff that I just couldn't incorporate because if I had gone down the path, it would have just taken way too long. And he also has this data science cheat sheet, which is really valuable to understand what question you're asking, what type of problem that is, and then what type of algorithm to apply to it. So that is always, if you're going down this road and you want to play on your own, that would be a couple of other good resources to look into too. But certainly going up to ML Studio and playing around, it's worth a look. It can be kind of interesting. I guess we got an evaluation form to complete too, but is there any, I guess we have about 14 minutes left, so it was pretty quick. And for this part, I'm going to bring Danielle back up, because Danielle is the data scientist who usually has to help me with the questions at the end.
Yeah, and there's some microphones if you, we can also repeat the question for the recording. Yep, awesome. Yeah. So the question is, how do you know which of those features that go into the model are actually important? Going back to like which features are relevant. Maybe you didn't know ahead of time. So it's called permutation feature importance. So there's a module that's built already to do exactly that. Basically, after you've already trained a model, you bring that module over and feed the results in, and it actually rank orders the relative importance of the different features. So if you look up permutation feature importance, and we have some blog posts around it as well. Yep. Question? If you retrain your model and for whatever reason you don't like the results of that, is there a way to fall back to the previous?
So there's a step in retraining is you retrain it and then you test it against your existing model and the new model it just created. And only when you feel confident that the new model that came out is better than your original that you overwrite it on the endpoint.
Yep.
So it doesn't happen automatically because that would be a disaster, right? If you're just playing around with it and it fails, and now all of a sudden it's live in your surface. Yeah, that would be a disaster.
Yeah, so not directly, but basically how you do that is you store the results somewhere and then you connect Power BI to it. So you put the results in a SQL database, for example, then you connect Power BI to the SQL database, and then it can automatically refresh over time. So you do that through some sort of storage layer. Question here? Yeah, so you would do that through human input into how you create your features. So in the example that Dan showed here is pretty simple of, you look at the raw temperature, the raw voltage, and those are your features that go into the model. In practice, what you have to do is this step called feature engineering, where you take the input variables and you actually create some other features. So maybe it's not just the temperature at that point in time, but the temperature over the last day. And so instead of having just temperature in your model, you might have another feature that's like temperature over the last day. And so similarly, if there was something like across devices, you may have a feature that's like average temperature across all the devices at this point in time. So you can create extra features that go into the model.
Absolutely, and then how you would apply that in the real world is your raw sensor readings are just getting pushed in through Event Hub or whatever. They go into storage, but then you use your HD Insight cluster or your SQL data warehouse to then create those aggregates along with the current raw readings to build up the set before it gets pushed over to your ML model.
You would have to, yeah, you would have to code it. I mean, we do this pretty much every in real production scenarios, you have to code whatever you want to do in that case. So if you want to look at that sequence over time in some particular manner, you would either do it outside ML Studio, use some sort of processing before you get the data into ML Studio, or you could use R, Python, special code to get out with whatever feature you want. So it's a special thing, but it's definitely doable. Let's take some question from the...
Yes. Is it possible to download the model for offline use?
That's a great question. So it's not possible. So this is all on cloud. For an on-prem advanced analytics offering, Microsoft has R within SQL Server 2016.
Okay.
So it's possible to do on-prem, but this is all in the cloud, and the model it lives in the cloud.
All right. Thank you.
Yep. And maybe let's take a question from the other microphone.
Sure.
All right, so are you able to see a representation of the model that gets created? So for example, you use the decision tree. Are you able to see inside of there what decisions it's making based off your features?
Yeah, for the high level things like number of trees and things like that, you are able to see that. For the details of the actual code behind the algorithm, you can't see with those algorithms. If you want to really create your own, you can create your own using R or Python. But you do get to see the high level decisions that the model made.
Right.
Gotcha, thanks.
When will you have machine learning in the cloud?
I don't know. It's a good question. You can follow up offline and I can connect you.
Other input sources like images, sound, video.
Yeah.
What's the story about that?
Yeah, that's a great question. So today it takes in raw data, and I believe you can also upload images as of recently.
As a byte stream, right?
Yeah.
There's other services, so Azure Media Services can do things like image recognition, stripping text to do stuff like that for you, but yeah, I'm not sure where you're at. I mean, you can obviously push it up, but then you'd have to train your model again on, byte streams.
So it depends on what you want to do, and yeah, if you follow up with us offline, we can connect you with some folks.
Thanks.
Can you have multiple training set? So if I have multiple customers, they might all use the same experiment, but for this customer, 70 is too high, and for this customer, 50 is too high.
Yeah, that's a great question. So how you would do that most likely is you would create one experiment with a main model, as long as they have the same data schema, and then you'd actually create different endpoints.
Yes.
So instead of having just that one endpoint, you'd have an endpoint per customer, and then you would actually use the retraining API to retrain those specific endpoints for that specific customer. So as long as your labels are tuned to those differences between the different data sets, then the model would automatically learn those differences and be tuned for that, and then you'd have a unique endpoint for each of those customers.
Great, thank you.
Yeah.
Hi. I was curious if batch execution supported large data sets. Like if you had a terabyte of data, is there like a cluster behind it, or is it limited to a single machine memory?
It is limited to, I don't know the exact specifications, but how we deal with that in practice is we create more endpoints and then parallelize through Azure Data Factory. So you probably wouldn't want to send that terabyte into one job. It would take too long. So it doesn't do the automatic parallelization today, but you can do that yourself by doing those multiple endpoints and concurrent calls. I don't know if you have other recommendations.
Yeah, I mean, that's what I would do. I'd break out your storage into maybe readings coming in based on region or customer,
Yeah.
and then have those executed per region or per customer so that it was parallelized. I mean, if it takes you 2 days to get an answer, that's not really going to be helpful.
Yeah.
So breaking it down. But if you want, you can follow up on offline too, and I can look into some more of that for you.
Thank you.
Time series pattern recognition. So you can definitely do a lot of time series work within Studio. So there's time series models within R and Python. AML Studio doesn't have particular time series models like ETS and ARIMA and so forth, but you can also reformat your time series question to be a model, to be something that you look at with the regular modules too. So that's definitely something that's possible. Yeah. Mm-hmm. Yeah. So that's
Yeah.
a great question.
We can totally do stuff like that, but again, this is
Yeah.
a really contrived example to not get too deep into the data scientists, because it really is meant for engineers like myself who,
Yeah.
the data scientists can certainly tell you, right? Oh,
Yeah.
it's in error because the temperature is high or because it's spiking during the day,
Yeah.
and we want to flag it. And by the way, we also know, because we have a bigger training set, that whenever I see this, the device is going to fail in the next 4 days. So within the next 4 days, you better fix it or something bad's going to happen.
Yep.
So you can certainly do those types of things, but for this example, it really is I wanted to keep
Yep.
it simple. I didn't want to get bogged down into the math or the statistics or how you
Yep.
do other
Yep.
features.
If you wanted to, you'd probably have to reformat the actual, going back to Dan's point about what question are you even asking. So it would be completely different than this scenario, most likely. You'd have a different label that was like your root cause. And then you would be predicting root cause. So you would say, so state would be one input variable, maybe temperature and voltage are the other input variables, and then your label, that what you're predicting is something like, the device had this problem, the device had this other problem. Maybe there's 10 of those example types of problems. So you would have to have that historical data with that label in it. So you'd actually be probably predicting something different rather. So it would be a completely different question than what was asked in Dan's demo. But it's definitely possible. It all goes back to having the data that you need for it and creating the model to predict that label data point. Yeah. You could definitely have thousands of features.
Thousands and thousands.
There is some upper limit. I don't know exactly what it is, but most examples, the number of columns that you feed into ML Studio is fine. So you can definitely have a lot more than what was shown here.
Yeah, and that's where all that work that I was talking about in the beginning between your subject matter expert, your data scientists, your engineers to try and formulate that. So what is the question? What do we have for data? How do we filter out the stuff we don't need, keep the stuff we do need? And that's where a lot of that work comes in.
Yeah. Michael?
Yeah. When you're using your machine learning for predictive analysis, and then once you've used your learn set to make a prediction, and then you preempt it, how do you prevent the new state of events from affecting the accuracy for your future predictions? So it fails every 3 months. Well, you stop it from failing. So now does it think it fails every
Yeah, it's
2 months and 3 weeks?
It's a really good question. So you do have to go back to retraining.
Well, I know you have to retrain it, but how do you not lose accuracy in the cause of the failure?
Yeah,
Because-
you probably will
Because
slightly.
you replace parts, you get better quality parts, or whatever the context is.
Yeah, you're changing the underlying how everything works.
So
probably
is it like a Six Sigma kind of thing where you just have to get
Yeah, it is.
more accuracy?
In a way, yeah.
Okay.
It's a hard problem to deal with.
Okay.
The feedback loop
Yes.
changes the underlying process,
Yes.
and then you don't have as many examples.
Yep.
Yeah,
Right.
so it's definitely a hard problem to deal with. In the failure prediction scenario, what you
Mm-hmm.
can often do is instead of predicting failure itself, you predict a precursor to failure. So maybe you don't have as many failure examples, so you have to actually change what you're modeling after you've started to improve the system.
Okay, so
Maybe-
you don't feed it like a false positive
No,
on
I-
purpose to say, when I replace the part, we'll call that a failure, but I fixed it so that it will show up as a failure?
I think it depends on the domain. You'd have to think
Okay.
really carefully about it, whether that was a valid scenario or
Okay.
not. I wouldn't just blindly suggest it, but maybe for a
Okay.
particular.
Yeah, that sounds like
Yeah.
really a hack. Okay.
Yeah.
Thank you.
Yep.
Warren, excuse me if I missed it, but on the model output in the service, do you get confidence values?
So you get the probability on a 0 to 1 scale. So he just took that scored label
Yeah.
and left out the probability, but the probability will tell you what range. So if it's like a 0.01, that means you're really close to predicting 0. If it's a 0.99, you're really close to predicting 1. So it's not actually a confidence, but it gives you the level towards the two ends. Yep.
Okay, thank you.
Hi, Dan. So I'm an engineer, and I
Yep.
know my business reasonably well. I've worked with data quite a bit, but I stink at statistics. So when I think about, okay, there's this whole art and science of data science, but I work for an e-commerce company. I maybe only need the 80%, not the 100%, value from this.
Yep.
So do engineers still have a place to at least kind of like start the company getting some small level of success with using these algorithms and so forth, and trying to learn basics of data science?
Sure,
Or is it,
absolutely. So you take some of the stuff I talked about, data science for the rest of us, that Brandon's talk is a good place to start. And then just go on to ML Studio and start playing with data. You know you have the data, so using some of those rules or guidelines we set around it, start bringing it in. And again, is it a classification problem? Is it a multi-class? Is it a two-class? And just start playing with it, and then you can try it out. I mean, yeah, the data scientists in my office, I leave a lot of that up to them because I'm building those pipelines with the intelligence suite. But absolutely, there's a place for engineers to go up and play with it. Again, it's free. I recommend everybody to try it, because if you're working with data science or data scientists, it's good to understand how these things come together. So, you're not like me 2 years ago where they start mentioning these keywords and I feel completely lost.
thank you.
Question?
Does the platform allow you to publish the same model in different regions?
Same model in
Different regions.
Different regions. Oh, so you can have workspaces in different regions, and that when you publish from a workspace, you publish the web service in that region. I don't think there's a way to publish a web service in a different region from that workspace.
You can share
So-
an experiment from workspace to workspace.
So you would create you can't create those underlying workspaces in different regions. Right now, I think there's Europe, Singapore, and US. So you would create a workspace in that region and then publish the web service from that region.
We're getting confirmation from Vivek.
Yeah. Okay, nice. Yeah. So what you do is you create extra features that represent those important things. So you'd create a feature that represented the season. You'd create another feature that represented something like day of week. So you could actually create extra features that can go into the model that can capture that variability. So a lot of that can be done on the feature side rather than the model side, like you're creating features that capture that seasonality, and then the model will automatically pick up the seasonality. There's also models that can inherently capture seasonality. So there's a few different ways to approach it, but the most straightforward is creating extra features that represent the seasonality that you put into your data. I think we actually have to wrap up, so maybe one last question, and then we can also follow up with people outside.
Yeah, we can go to the speaker area.
Yeah, yeah.
Are there any specific versions of Python you guys target on the interpreter side?
I think there's both Python 2 and 3.
Okay.
I'm pretty sure there's both. I know that the notebook, so Dan showed mainly the drag drop, but there's also Python notebooks. And there's definitely both 2 and 3. For execute Python, I'm actually not sure which one it does.
Thank you.
Yeah.
2.
Okay, the execute Python does Python 2. Thanks.
That's either 2 or piece.
Okay, thanks everyone.
Thank you.
Catch up with you.